We often wonder where we might find a truly sustainable and abundant source of energy, and the answer might turn out to be in the emptiness all around us. Today we'll be looking at zero-point energy, with a particular emphasis on the type known as vacuum energy and the Casimir effect. And as usual, we'll be aiming to make these concepts a lot simpler and intuitive, rather than the mysterious technobabble presentation they tend to get in science fiction, and sometimes even in science. We are going to be discussing some sci-fi examples though, so if you ever wondered how the ZPMs of Stargate SG-1 worked, grab a drink and a snack, settle in for a bit, and hit those like and subscribe buttons. To understand anything involving zero-point energy or vacuum energy, we need a little bit of quantum mechanics, and critical to that notion is that the universe seems to have its equivalent of minimum-sized building blocks or pixels, stuff that you can't cut in half further, not able to be divided more, which is what the term atom means, although we later found out you could go to protons, neutrons, electrons, and the proton and neutron down into quarks. You've probably heard that a proton or neutron is made of 3 quarks too, and this is mostly wrong, and we'll get to why shortly, but the reason why it's wrong is critical to our topic today. Currently though, we believe electrons are not divisible and neither are quarks, that they are fundamental particles, though plenty of theories like string theory or M theory contemplate a smaller or more fundamental particle beneath them. However, the basic and fundamental indivisible thing of quantum is not size or energy of a particle. Rather, it's always some pair of complementary traits. You will probably have heard of Heisenberg's uncertainty principle and how we can only know the momentum or speed of a particle or what its position is at the same time, with so much certainty. Conceptually, you might imagine you want to measure some object's speed and location, and you can only do this as well as your instruments allow, say a stopwatch and a ruler, each accurate to a millisecond and a millimeter. And if you want to do better, you'll need to buy more expensive and accurate equipment, but you have a limited budget, so buying a more accurate ruler or stopwatch means having to buy a cheaper and less accurate type of the other, giving you a maximum accuracy or minimum uncertainty you can reach with your available equipment. In the case of the Heisenberg uncertainty principle, we have a minimum uncertainty that the universe budgets us for measuring these 2 paired traits, momentum or speed with position. That represents a type of fundamental thing, or pixel if you would. There is an inherent uncertainty to any measurement of any particle, but not based on one trait like how wide it is, or how much energy it has, but rather as the product of 2 traits which are conjugate pairs, like momentum and position. That minimum value is Planck's constant, and is in units of energy times frequency, or mass times speed times position, and it turns out that same value works for a number of other paired quantities, like energy versus time. We can only know so accurately how much energy something has by sacrificing how accurately we can time its existence. There are many more. Angular momentum with orientation or angular position is one. We have magnetic potential with density of electric current, and electric potential with density of electric charge, or gravitational potential with mass density, and more. But the big one besides momentum and position is energy with time, and contemplate for a moment that the universe allows us to have an uncertainty of energy at some place, because we can only measure it so accurately. We cannot say it is 0, even if nothing is there, because there is that uncertain value of energy at any given moment. The bigger that amount of energy is, the shorter the moment it can last, but that packet of energy is a particle. This shows up in a lot of ways, and one of those would be with a cold classic particle. Heat and temperature indicate random kinetic movement of particles around in some medium or place, and we cool things by leaching out that random motion. In theory, if you leach it all out, your system is at absolute 0, which is negative 273 Celsius or negative 460 Fahrenheit, and the Kelvin and Rankine system are the Celsius and Fahrenheit scale where we set 0 as absolute 0. So today as I write this episode back in July of 2023, it is 88 Fahrenheit or 548 Rankine here in the US, and in Celsius or centigrade, that's 31 Celsius or 304 Kelvin. Absolute zero has some weird hypothetical properties, like possessing no entropy, but you cannot actually get there because of the uncertainty principle. If your particle was totally without momentum, we couldn't tell where it was in terms of position or vice versa. The key thing about the uncertainty principle is to understand its real haziness of location. For instance, if I have a prisoner in transit and the prison transport breaks and he escapes, we can estimate how far he might have traveled on foot by knowing how long it's been since the crash and how fast he might be able to walk. And he might be anywhere inside that circle centered on the crash, and with a radius equal to his maximum speed multiplied by the time since the escape. His position is hazy and uncertain until we find him, but he's classical, so the uncertainty was only to us. He had a real and specific course he followed and was never at any of those other spots in the circle. In quantum, until we measure something, it truly was in all those other places, less a specific object and place than a fog or haze across it all till it actually pushed into a more certain state. And again, this isn't just position and momentum, but any of those conjugate pairs like energy and time. That's the really weird part about quantum, adjusting to the notion that the uncertainty was real, a fundamental minimum of the universe, not all limitations as observers doing measurements. Some folks like to think of it like a pixel. I tend to refer to it as a minimum accounting limitation, like we don't have fractions of a penny. If you've seen the film Office Space, which is a bit of a cult classic, you might remember that their get-rich-quick method came from stealing all the half-cents or fractions that were done in billions of trades. Every transaction, whether it was for $1.02 or $1 million and 7.5 cents, had one of the parties getting the whole cent and the other not, and they were grabbing that for themselves. Keep that notion in mind, because in a lot of ways that's the notion behind harnessing energy from quantum uncertainty. But zero-point energy derives its name from absolute zero, and the idea that even perfectly frozen atoms or molecules retain some vibration and thus energy, and we extend it out to all sorts of other phenomena who have fluctuating fields of some sort and energy that would exist inherently in them from quantum, and call this 0 point. And it doesn't even have to involve any normal particles, which is where vacuum energy comes from. Even in the emptiest seeming bit of space, far from any planet or star or even galaxy, there's still traffic moving through there. Think of an empty rural town with a major highway going through it. Its population might only be 100 folks, but several thousand people drive through there every day and are a fractional resident, as it were, living there for 5 minutes. And so every 288 people driving through in a day makes for one more all-day resident. Even in the emptiest bit of space with just a gas particle or hydrogen atom per cubic meter, there are still billions of photons and neutrinos pouring through there at any moment. It's not a real vacuum as a result. But it goes beyond this, because space has a lot of what we call virtual or temporary particles popping in and out of existence. And these are very important because they are what you and I are mostly made of. You've probably heard that each of your protons or neutrons in each of the atomic nuclei in your body are made up of 3 quarks, but if you ever looked at the mass of those quarks and the mass of a proton or neutron, you'll notice there's something off in the accounting. We generally measure a particle mass in a unit called the mega electron volt, or MeV for short, as opposed to kilograms or pounds. But an electron mass is about half a MeV, whereas an up quark measures about 2.3 MeV and a down quark about 4.8 MeV, about 5 and 10 times more massive than an electron respectively. Protons are 2 up quarks and 1 down quark, neutrons are 2 down quarks and 1 up, so you expect the neutron to weigh a couple MeV more, and that is the case, except you expect they weigh something like 10 MeV from that. And in reality, a proton is 938.3 MeV, and the neutron is 940.6 MeV, around 100 times more massive than we were expecting. Where is that mass, and what allows these things to shift their form, or interact with each other to divide, or combine or change into other materials? We discussed this more in our Antimatter Factories episode, but the short form is that we have both valence quarks, which are those 3 known quarks, and a lot of gluons and a sea of virtual particles, including virtual quarks. You might recognize valence quarks from chemistry, where we have the valence electrons, the ones in the outermost shell of an atom that actually bond and interact with other atoms to form molecules, and about the only part of an atom seen and interacted with in the higher chemical layer of reality. Think of those 3 valence quarks in that regard. They are the more stable bit of a particle, like a proton or a neutron, that has any meaningful stability in that next higher layer of reality. You might also think of them as an iceberg floating on a larger sea of water, not really permanent but more of a real object than the random volume of that water. That water is still very much there and real, and pushing all those icebergs around, but other than some rippling waves, we don't really see it much from above. But we might see one of those waves, especially if a large iceberg chunk or rock fell in to make a ripple, but it's kind of debatable if that's an object. Virtual particles are like that, and in general they pop up in opposite pairs and annihilate, and they often have properties that would not normally exist in a stable form. Just as an example, it might be that particles could only have an energy state between 1 and 1 billion eV, and we found they almost always lasted for only the barest fraction of an instant as such a packet, but that for some reason those at 511,000 EV lasted quite a while, and those at 2.3 million and 4.8 million did too, and also at 95 million and 1.275 billion, those being the masses of the electron and its positron antimatter twin, and the masses of the up, down, strange, and charm quarks, along with their respective antimatter twins. We do not know why, though there probably is a reason, and it might be something along the lines of why very few numbers are prime numbers or perfect squares, and fewer at bigger numbers. Things we think of as constant and immutable at that higher atomic layer of reality beneath the chemical but above this subatomic particle realm, like having a positive mass, are no longer guaranteed, and you might have a pair of particles that had positive and negative mass rather than positive and negative charge. Incidentally, we discussed more about pair annihilation and apparent time travel in our recent episode Retrocausality, and we'll mostly bypass that for the sake of brevity today, since this episode is long enough already. Such things are always popping in and out of existence everywhere in the universe, all of the time. They exist for a moment, then annihilate again, and indeed the virtual particle pair is arguably more of a concept we use for describing it than a true reality, like the planetary model of atoms, handy and decent for describing a concept with no clear analogy to our layer of reality. And again, we discuss that more in Retrocausality. You could just as easily think of it as a quick ripple of a wave on that sea with a given height and frequency, and next to it a drop in height, a negative valley between waves, though not an absence of water in a true negative sense, just a local negative, with a kilometer of sea below. All reality, from the atomic and above, floats on that sea, the Dirac Sea, and might bob and dip a bit, a few feet here or there, but the ocean below is kilometers deep and not in any way a vacuum absent of mass or energy. Our knowledge beyond this gets increasingly murky, like staring down into an ocean, but we assume somewhere deep below is the true bottom, the true vacuum, and as you might guess, our interest in accessing this false vacuum, the ocean of space as it were, for energy and resources is quite high. Key notion though, empty space contains energy simply by existing, much as a volume of ocean contains water. It may contain all sorts of other things and energy, but that basic existence, even when emptied of others, still represents energy and vast amounts of it. Folks wonder why black holes can lose mass over time, since nothing can escape, and they will hear that they can evaporate by losing virtual particles. It will then seem strange to hear this happens at their event horizon, and the bigger that horizon, or the bigger that black hole, the slower this goes. and the reason is because that black hole isn't the source of those virtual particles. Regular old space is. There was no greater amount of virtual particle pair production at an event horizon's surface, but tiny ones have very sharp changes in gravity compared to big ones. If one of the particles in the pair is even a nanometer closer to the black hole than its twin, it will experience vastly higher gravity pulling on it. And what that means is that if two particles pop up, one on each side of that event horizon, one can fall back in. This is the one with negative mass, for reasons we'll skip today, but have discussed in other episodes. The negative mass one is pulled down while its positive mass twin escapes. They do not recombine and annihilate, and the black hole loses a little of its mass. Most of the time, even there, this does not happen. They're close enough together to annihilate even with one of them experiencing a stronger yank down than the other. But the sharper that difference, the tidal difference of gravity, the more likely this is to occur. When one of those particles doesn't annihilate with the other, they stick around and become real, so to speak. Real and virtual particles are pretty vague terms here, and again, these are more usefully thought of as thinking aids for visualization than anything else, so you have to be careful stretching analogies here. But this is one of our first ways we could get energy out of the vacuum of space, and that's by letting it get ripped out of black holes. Stephen Hawking is famous for many reasons, but his work on black hole evaporation is what he originally became well known for in physics circles, long before the general public had heard of him, and we call this radiation coming off them Hawking radiation as a result. Small ones emit more and die quicker, and one the mere size of a proton is giving off a gigawatt of power, by our equations, which have the radius of black holes change linearly with their mass and their lifetime going inverse cube of that. And such a gigawatt-powered proton-sized micro-black hole would still mass an incredible 560 megatons and still live 480 billion years, 35 times the current age of the universe. Let me put a caveat on there though, and a couple more of them. First, we have no experimental proof of this, which is why Hawking did not have a Nobel Prize. And second, it's where we start running into those quantum gravity issues we talk about where Einsteinian relativity runs into quantum mechanics and doesn't seem to agree or match well. So, we don't know how deep that sea is or how dense matter can truly get. We're not so sure black holes really are point-like singularities at their cores, but at a certain point the amount of energy radiating out of one in a given instant might rise so high that it peaked out, because you couldn't get any more virtual pairs popping out of that ever smaller volume to keep up. The well runs dry, or at least the water can only come out so fast. How deep that well is represents another big problem, because general relativity and quantum disagree, and by many, many orders of magnitude, with the 2015 measurements being about 55 orders of magnitude smaller than the theoretical vacuum energy density. 55 orders of magnitude, to give some scale, is more than the difference between a proton's radius and the radius of the entire observable universe. So a bit of a disagreement there, and definitely not as accurate as we would like. If you want to describe something's size and say it's somewhere between smaller than a proton and bigger than the universe, plus or minus a few more orders of magnitude, people might tend to wonder if you know what you're talking about. But what we are talking about is the density of that vacuum energy. Currently, the low-end figure is somewhere around 3 or 4 hydrogen atoms worth of mass energy per cubic meter, and the higher end is a billion times denser than a neutron star. And this is the depth of our ocean, our Dirac Sea. It is somewhere between a shallow lake not much deeper than the gentlest ripples on it, to one so deep that even a tsunami is barely noticeable against its endless depth. And it makes a big difference which one of these is right, or if it's somewhere in between, for ideas of tapping vacuum energy. Now in sci-fi terms, vacuum energy and zero-point energy are pretty interchangeable, and again in science terms, vacuum energy is a subcategory of zero-point energy. And if we consider the ZPM or ZPM, the zero-point modules of Stargate SG-1, we get a description that sounds specifically like vacuum energy. It is fictional, of course, and we hear it described as a pocket of subspace that's been crammed into the ZPM, which is a cylinder the size of a large thermos, and can be carried around, but provides untold gigawatts of power for centuries or even thousands of years. That tends to imply the device has more energy in it than its mass energy would indicate, though it's hard to say. A 10-kilogram cylinder slowly draining itself of mass energy could provide 2.5 gigawatts of power for 10,000 years, similar to the largest power plants and dams. And in that TV show, we see the island city of Atlantis submerged for 10,000 years, running on minimum energy, protected by its energy shield, and that's how long it had to run in order to drain 3 of those ZPMs dry. So maybe the modules only have mass energy, like antimatter or a micro black hole have. That might be in there by stuffing it with condensed pockets of space-time, but don't assume a big condensed pocket of space-time does not have mass. It has energy. You don't have to carry it around with you, and doesn't have any real drag effect as you fly through it, kinda, but that doesn't mean that if you jam a cubic light year of space-time into some module that it wouldn't have mass. That Sci-Fi franchise has wormholes though, so maybe it's connecting to a micro-universe or pocket dimension they made, and that connection or universe is slowly destabilizing or draining, and that module is just the hardware needed on your side. It's the power outlet, not the power plant. Generating power by harvesting space-time, which seems to regularly spring from nothing as the universe expands anyway, wouldn't seem to require carrying it around, though you might need some sort of pressure difference. Much like a lukewarm bathtub has tons of energy, but you can't generate power from that tub unless you have some lower temperature or pressure region to drain it into. That might be where you need some sort of pocket universe, as opposed to just crunching down local space-time, which, as mentioned a moment ago, might be anywhere from needing a cubic kilometer of vacuum to generate 1 joule of energy, to needing the volume of a typical water bottle to generate the energy output of a supernova, which is even more ridiculous than the already huge amount of mass energy a bottle of water has, exceeding the typical multi-megaton hydrogen bomb. We cannot tap that bottle of water for power very easily though, and the same would seem to apply to the vacuum. Let's get to tapping that energy, and we'll begin with the Casimir effect, which we should start by saying is an effect we've done in the lab plenty of times, as I know a lot of this stuff sounds very sci-fi and can make you wonder how glued in it is to real experimental data and results. In the Casimir effect, we notice that 2 very flat plates, kept within a very short distance of each other but not quite touching, will have a force or pressure pushing them together. This will happen even in a vacuum chamber. This certainly seems mysterious, but in the virtual particle context, we need only remember that these particles have a wavelength based on their energy. The more energy a particle has in it, the lower its wavelength and the higher its frequency. A particle with a very long wavelength cannot form between 2 plates that are closer to each other than that wavelength. It's too big to cram into that spot, while ironically smaller but more energy-dense ones can. If you start with those 2 big plates very far apart, though no further apart than they themselves are wide, you will notice a little force pushing them together, but only a little. And that's because those very wide wavelength particles are still forming outside of it and bumping into the backside of either plate occasionally to give a small shove, but there's no shove of that wavelength or higher from inside. No perfect balance and thus a net push inward. As they get closer, more and more wavelengths are getting excluded from forming between them until eventually almost none can. The pressure outside is normal for a vacuum, but somehow the pressure inside is less than 0, and now we know this is from that false vacuum. The space outside is not really empty, the space inside those plates is just emptier. This is measurable in a lab, the Casimir effect, and is one of the ways zero-point energy and vacuum energy first got identified. Whenever you hear folks talking about negative pressure or negative energy levels being observed, this is usually the situation being referred to, and again it's -1 like -1 Celsius is, as opposed to -1 Kelvin, or how being 1 foot underwater is -1 foot, when that ocean is miles deep and the planetary core 4,000 more miles below. It's not less than nothing, it's less than the local normal. Nonetheless, while it is less than the local norm, it might be sufficient for some of the suggested uses of negative energy or pressure, like holding open the mouth of a traversable wormhole or running a warp drive. Now, this isn't a lot of power being produced, arguably none, This isn't likely to ever practically produce power with known material, too much friction issues for a very weak force. If you have access to something like mag matter, which would allow flat plates fine enough to be flat and separate way below the conventional atomic scale, this might work. For anyone wanting to run the calculations, the idealized force goes with the inverse fourth power of distance between the plates. So make your plates 10 times closer, and the force gets 10 to the fourth power, or 10,000 times stronger. The force is the pressure times area, so it grows linearly with the area of the plates. We usually say you need those plates to be within about 10 nanometers to get a -1 atmosphere of pressure between them, and we might imagine a pair of graphene sheets that could achieve a mere 1 nanometer separation and have 10,000 atmospheres of negative pressure. That's 100 times the pressure difference inside the piston of a race car. So you can imagine devices at this scale being able to produce serious and usable levels of energy, if you can find a way to tap it. But I am hand-waving a lot there about managing to get improbably large plates improbably close to each other and doing it in some fashion that you can generate net useful energy from and quickly. This could make for very tiny power generators, those smaller than biological cells and yet much more powerful, the ideal nanobot power source. More likely you would be looking at far lower pressures and far larger surface areas, like kilometer-wide arrays of panels operating at the low nanometer scale in some very vibration-proofed ultra-cooled vacuum lab in deep space. And assuming you can even generate power this way at all, this is hotly debated, it's the sort of thing you would use for some extragalactic post-biological civilization running on computronium, far from another power supply and with access to all the space they want. Let's move on to some other vacuum and zero-point energy options. Though let me note first that this isn't necessarily limited to power production either. The particles you potentially can rip out of the void itself don't always have to be photons. They might be more mundane particles of matter, or exotic ones. And I should note that quarks never exist by themselves. They always have a gluon connection to at least one more quark, or if you pull a pair of quarks apart, the force needed to rip them free from each other is exactly the energy needed to create another pair of quarks, so that you now have two pairs of quarks. You broke them apart by applying enough energy to pay for the mass for those two new ones. So let's talk about the infinite hotel paradox next, also known as Hilbert's Hotel for the famous mathematician David Hilbert, who discussed the idea 100 years ago in 1924. In it, we assume a hotel with a countable infinite number of rooms, and each one is occupied. We just said every room is full, so infinite rooms or not, it can accommodate no more guests. But infinity is weird. No matter how big a number you count to, there is always a bigger one. So if it has infinite rooms, there should always be an empty one, and there never is a last room either. So the manager should be able to find you a room as you enter by having each occupant move one room over. Room 10 goes to room 11, who goes to 12, and room 1 trillion goes to 1 trillion and 1, etc. You go into room 1. By this same reasoning, if the hotel starts having guests exit, each leaving by moving first to the room one number lower than them, then an infinite number of people can exit. This is our mathematical justification for how we could potentially pull infinite particles or energy out of vacuum energy, and stuff them back in too, as the Dirac sea is assumed to be infinite. And in this case, can I pull electrons right out of the vacuum and back in again, but generate current whilst I do it? Stepping a bit more into hypothetical physics, we have a class of particles known as fermions, named for the same Enrico Fermi as in the Fermi paradox, and along with bosons they make up all the particles and matter we know of. Bosons, which include photons, are mostly noteworthy for being allowed to be in the same place as other bosons, which is handy since the extreme low frequency, high wavelength photon might be the size of a planet, while containing a billion trillion times less energy in it than an electron, which is a type of fermion. Fermions are particles that can't be in the exact same place as other fermions, or specifically the same quantum state. Normally a fermion has an antiparticle, much as the positron is the antiparticle of the electron, and we call any of these Dirac fermions, and all the standard model fermions except neutrinos are Dirac fermions. But we also have a hypothetical particle called a Majorana fermion that is its own antiparticle, and it's debated if the neutrino is one of these. Majorana fermions come up in a lot of superconductor discussions though, as you might have noticed with the recent discussion of LK99, and particularly in the MZM or Majorana Zero model, and there's also some question on if they might violate conservation of energy. There is research indicating that the number of these types of fermions that exist matters. For instance, if just one type of these fermions exists, when moving through our boundary it could disappear into nothingness. That's interesting if one wants to get rid of energy, but not so useful for energy generation. And then again, math is unforgiving and unempathetic, and if in some situations it would allow for energy to be lost, then so too one can imagine energy could be gained. Producing these fermions out of nothing at the boundaries between different materials doesn't sound too interesting, but we need to keep in mind that if one can't produce matter, we can produce or keep alive black holes, which could be used for direct energy extraction. There's a lot of aspects of quantum that seem to leave the door open to violating conservation of energy, or allowing power production that might seem to be a perpetual motion machine, or draw power from outside our conventional physical universe. These generally would count as either vacuum energy or more broadly zero-point energy. Recently, the discovery of the gravitational wave background makes relativity also a slightly better candidate for energy extraction out of the void. Like waves on an ocean that through their mechanical action are able to generate useful work, we might find ways to tap into this universe-wide ocean of gravity waves. One possible way to get energy from gravitational waves would be using resonant mass devices. These are devices made to resonate at specific frequencies. If gravitational waves passed through them, they'd start moving, or amplify the movement they already have. Tune them just right to the frequencies of the void, and we could get devices that move in an orderly fashion that we could use for creating electricity or for their mechanical energy directly. Indeed, if we could get ourselves to move at higher speeds, then the frequency of the gravitational wave background would increase, same as blue-shifting cosmic microwave background radiation, since like on an ocean, waves would hit you more often if you were in a boat traveling faster on the ocean. We could then get more energy out of these waves, with the only possible initial cost of accelerating at high speeds. If moving really fast, we'd also be able to extract energy from the other kind of background action, the cosmic microwave background radiation or CMB, which again would itself become more energetic from our perspective, though of course it can also have a drag effect too. Channel regulars will know I'm not a big fan of string theory, but it is one of, if not the strongest theory we have for exploring beyond the standard model. And along with M theory, both allow options for sparking of new big bangs, or brane collisions, or poking holes in the false vacuum to generate power through. And we've already discussed how some of those options might work. We also have other non-vacuum specific options for zero-point energy that might arise out of modified gravity theories, meant to explain either why gravity is so weak compared to other forces, or maybe is falling off in strength faster than we think, and eliminating the need for dark matter or dark energy. Dark energy also seems to offer a way of violating energy conservation at the grand scale. It's interesting to imagine some infinite power supply, possibly a very weak one, requiring lots of space to get a useful output, as it can have some effects on civilizations we might not expect. And let's close with some of these. First, we might imagine a big vacuum energy power generator helping run a spaceship, but we also might imagine one that was simply using weakly interacting particles like neutrinos or dark matter ripped from the void as its propellant. Such an engine is safe to use around planets and inhabited megastructures, unlike another conventional engine spewing out vast amounts of highly interacting and highly energized particles that would often make a rocket plume seem weak in comparison. Second, while it obviously violates conservation of energy, there's not really a problem under Einsteinian relativity anyway, though one can argue if all that new energy contained in new bits of spacetime created by dark energy counts as a violation, or local violation anyway, and so too this would seem to violate entropy, but we should keep in mind that the Big Bang did too, and while we say violates, it's not like there's any apparent police force out there holding up the law. But it might be something more akin to vacuum energy having real limits on how much energy you can pull out of a given volume, in which case our conventional notion of Dyson spheres and Kardashev 2 civilizations might be wrong, and maybe every alien civilization is very spread out, and favors extragalactic space, where it's bigger and cooler. They just grab what they need for the trip, leaving the galaxy fairly untouched overall, and head out, somewhat akin to the hermit shoplifter hypothesis of the Fermi paradox we'll discuss next month. This is a dubious caveat on the Fermi paradox, because unless this vacuum energy is miraculously generated in some way that removes its waste heat signature, we should expect to still see that huge infrared source representing someone using a lot of it. But if it needed to be small and diffuse enough, it could easily be so widespread and minimal that we're not really detecting it yet. Not invisible, just too hard for us to see yet distinctly from background noise and other ambient radiation, especially as it might be very close to cosmic microwave background radiation in frequency. It might be a bit hard to guess that frequency too, as folks leaving the galaxy to use it might be moving at a variety of high speeds, especially once they've been traveling long enough that Hubble expansion is speeding them up and red-shifting them from all perspective. Of course, to end with a note of warning and promise, a Pandora's box, it might be that the only really useful way to generate power from the vacuum is to puncture that false vacuum, and we tend to think that might send a ripple of spreading annihilation out at light speed from the puncture, replacing it with true vacuum, or a new universe. It may be that the answer to Fermi's paradox is that people learn how to use vacuum energy very early on, but they do it by making a new Big Bang in a pocket universe, which they can tap for power, like those ZPMs are implied to be from earlier. Maybe we exist inside one of those, or maybe the reason we don't see any alien civilizations is that every time one comes up, they wreck their region of the universe they're in, or create a new one. Maybe we are just waiting till such a wave of destruction reaches us, unless we blow a hole open ourselves first. Or maybe we're just the next in a long line of civilizations that blew themselves out of existence to make way for a new universe built on their ashes. Metaphorically, anyway. After all, what it's really built on is this infinite sea of vacuum, of nothingness, and if you can make matter or energy from nothing, well, that sounds like the sort of power a god has. And it might turn out you need to be in that tier of skill to successfully wield the living void that spawns realities. Either way, vacuum energy is definitely a place worth investigating, but where wise men might fear to tread, since it's very easy to fall when you're walking on nothing at all. Contemplating the fundamental underpinnings of our universe, like vacuum energy, does tend to lead naturally to thinking about the beginning of time and where we came from. That still remains an area of speculation, but we can look further back every year, and what we see is a dark age in between the early universe and the first stars arising, a period in which many critical properties of the universe were very different, possibly allowing unusual types of stars to form. And I thought we would explore that topic in another Nebula original, Dark Stars at the Beginning of Time, which is out now on Nebula, our streaming service. On Nebula, you not only get to see every regular episode of SFIA a few days early and ad-free, but all of our other bonus content, including extended editions of mini-episodes and more Nebula original episodes like Life as an Asteroid Miner, Nomadic Miners on the Moon, Space Freighters, Retrocausality, OR and Free Will, Conformal Cyclic Cosmology, Colonizing Binary Stars, and more. Nebula has tons of great content from an ever-growing community of creators. Using my link and discount, it's available now for just over $2.50 a month, less than the price of the drink or snack you might have been enjoying during the episode, and it goes to supporting new content from myself and other creators. When you sign up at my link, go.nebula.tv/IsaacArthur, and use my code IsaacArthur, you not only get access to all the great stuff Nebula offers, but you'll also be directly supporting this show. Again, to see SFIA early and ad-free, and with all the exclusive bonus content, go to go.nebula.tv/IsaacArthur. I want to give a quick thanks to fellow physicist Vlad Ardelean from the Infinite Energy Initiative for helping to write this episode. He and I had been chatting about that project just as I was getting ready to draft this script, and he volunteered to help and included some ideas for zero-point energy production, and it was perfect timing. Vlad founded the Infinite Energy Initiative to explore more way-out ideas on energy production like vacuum energy, and to bridge the gap between science and sci-fi. If you're interested in seeing how they plan to push science beyond its currently accepted boundaries, looking for new sources of energy like the ones we discussed, or would like to get involved, check them out at infiniteenergy.org. So next week we have 2 episodes exploring the fabrication of the future, starting next Thursday with a look at spaceship factories. Then it'll be time for Sci-Fi Sunday on October 15th, where we'll contemplate entire planets turned into giant factories in Forge Worlds and Industrial Planets. Then we'll ask the big question of if life extension is ethical on October 19th. Then we'll look at another type of dedicated planet, Fortress Worlds, on October 26th. And wrap things up on Sunday, October 29th, with our monthly livestream Q&A. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content at go.nebula.tv/isaacarthur. As always, thanks for watching and have a great week.